Okay, we are talking about slightly soluble salts today. So I'm going to kind of define this for you because slightly soluble salts might be a little confusing considering the fact that we usually classify salts as either completely soluble or insoluble, and there's actually some in between there. So in Chem 161, we said we have the set of solubility rules, and if you go by the rules, you can be like, okay, well, this thing dissolves and this thing doesn't. Well, of course we lied. It's not black and white like that. Because 162 delves into the equilibria of everything, there's always going to be a teeny tiny bit that dissolves of something that's, quote, insoluble. There's always going to be a limit to what can dissolve of things that are soluble. So that's where we're going to go in. So the solubility rules in Chem 161 were really, those were black and white, but they're really not black and white like this. It's not black and white. Essentially, everything can dissolve at least a little bit. Everything will dissolve. I'm going to put slightly. Okay, it's just what scale. Does it dissolve really, really well? Or does only a very, very small amount dissolve into the solution? So we're going to look at these slightly soluble salts, and they're governed by equilibrium. So we're going to have K values, just like we have with all of our other equilibria. So when we are looking at salts, okay, salts being ionic compounds, okay, so salts being ionic compounds, okay, when they dissolve, they dissociate, right? So these are all going to be based on dissociation equations. Okay, so if you look at the solubility rules and you see check for PbCl2, so one of the rules is chloride ions, so things with chloride in them, are always soluble unless they are with, and then there's 3 exceptions, one of those being lead. So per the rules, lead 2 chloride is insoluble, okay, meaning it won't dissolve. Now, in reality, it's just not very soluble. Okay, so if I write out, this is the dissociation equation. Dissociation equation, okay, which just shows what happens when it goes into water, it splits into its ions. It's essentially just a very small value. Okay, so a small K value means not very soluble, right? Because a small K value means there's not very many products because it's products over reactants. So that means it hasn't shifted to the right very much. Okay, so small K means it's not very soluble. All right. Again, so if you're trying to be like, put those numbers together, if I write a K equation for this equation here, it would look like this, right? Pb2 plus times Cl minus squared. Okay, and there's nothing on the bottom because this is a solid. So it's just the multiplying the concentrations of the ions, essentially. And so if this is really small, that means there aren't very many ions that actually went into solution. Most of it stayed as a solid. Okay, so this K value is called KSP. So you'll notice the little SP down here. We've had KA, we've had KB, KC, KP. The little letters at the bottom just denote what kind of equilibrium we're talking about. All right, so KSP is called molar solubility, okay? And this is the solubility product constant. That's what the S and the P stand for. So just still constant, K is a constant for specific temperatures, okay? And we calculate it with, the dissociation equation. Okay, that I just wrote above as an example. Okay, so it is the product, meaning multiplied, right, of the ion, so let's put of the ion concentrations, right? So like I said above, if I were to calculate KSP of lead chloride, it is essentially just the lead ion multiplied by the chloride ion concentration squared. Okay, so it is the product of those two, and it's always only going to be 2 ions that are part of that actual compound. Okay, so this term molar solubility, molar meaning molarity, right? This is a term we use to describe how soluble something is. Molar solubility is the moles per liter, so molarity, right? This means molarity. And when we're describing molarity, we use the term molar. It's the moles per liter present at equilibrium. Okay, so this is where this whole equilibrium thing comes in. We are, of course, then going to be using ice tables to determine how much there is at equilibrium. Okay, so molar solubility in regards to our ice table is X. So if I'm asking for molar solubility, I want that X value. That's how soluble those ions are. Okay, so it is important, and I kind of starred this because if you don't write your dissociation equation correctly, you are not going to get the correct value. For example, this one, chloride is squared, so you can't forget those coefficients in there. These ones are not going to be all 1-to-1 ratios like they were for acids and bases because we can have all different numbers of ions depending on what the charges are. Okay, so we're going to do example number 1 here. It says the KSP for calcium fluoride is 3.4 times 10 to the negative 11, so really not very soluble. What is the molar solubility? That means I want to find X of CaF2 in moles per liter, right? That's just molarity, capital M. Okay, so I'm going to write my dissociation equation and set up an ice table, right? Because this is all about equilibrium. So CaF2, when it dissolves, would break into a calcium ion, which is 2+, and 2 fluoride ions. You're always only going to have 2 things. Okay, there's a calcium and a fluoride in this case. There's always a positive thing and a negative thing. Okay, so I'm going to go with an ICE. This is solid, so that part actually doesn't matter. So you're always going to be able to get rid of that. I don't start with any ions, but when it dissolves, then I'm going to be plus X and plus 2X. Okay, so this one is going to be X and this is going to be 2X. Okay, so if I were to write the KSP, I'm actually going to write this out first. According to my equation, it should be calcium times fluoride squared, right? So then I'm going to put my equilibriums into my KSP. So KSP is going to be X times 2X squared. Okay, now algebraically, don't forget that this 2 goes to both of these things. So if I multiply this out, it's actually 4X cubed. Okay, so KSP equals 4X cubed. Well, I have the KSP, so it's really 3.4 times 10 to the negative 11th equals 4X cubed. And this is pretty easy to solve for X, right? Just divide by 4 and then take it to the 1/3 power. And you would get, in this case, that X is 2.0 times 10 to the negative 4th. And that is a molarity. These are ice tables. Okay? So this is what I was asking for. I wanted the molar solubility. And this is like the solubility of the ion. So it's 2 times 10 to the negative 4th molarity. That is the answer. That's it. I want you guys to try example number 3 and then check back. All right. So go ahead and pause it. Okay. So if you got 7.8 times 10 to the negative 12th, you did this right. I wrote out my KSP equation. I kind of dropped the ice table. I know this is going to be 2X and this is going to be X and KSP is going to be 4X cubed. The other piece of information I gave you in the problem is that the concentration of the Ag+ ion in a saturated solution, remember saturated solution means at equilibrium, is 2.5 times 10 to the negative 4th molar. So that meant this 2X value, which is silver, is 2.5 times 10 to the negative 4th. So I set those equal to each other, solved for X, then plugged it in and got my KSP as 7.8 times 10 to the negative 12.